Hiya, Michael here with a quick video how a dynamic microphone works. And what we're going to do is talk about the magnet and how that's made and what it looks like, the coil, how it's made and what it looks like, how they're put together, and then we'll have a look at the physics of how it works. So this is what a dynamic microphone looks like. It's also sometimes called a moving coil microphone. And this bit is the physics. If you have a coil and a magnet that move relative to each other, when you have a circuit, a current flows. And you should know the convention known as Fleming's right-hand rule. We'll come to that a little bit later. Right, let's straight away have a look at the magnet. Now, the magnet is made in the shape of an annulus, a permanent magnet, plus a soft iron pole piece. And when they're put together, the permanent magnet, this part, north pole at the top, south pole at the bottom, it induces the pole piece to become a south pole. So when you look at it from on top, this is what you see. North pole around the outside, south pole in the middle, and of course the magnetic field, we say, goes from north to south, so it's what we call a radial magnetic field. And that's important, as we'll see a little bit later. Now let's have a look at the coil. Now the coil is made on a very, very thin plastic former. There's a picture here. You can see the diaphragm on the outside and the coil is wound on this former. So here's the diaphragm, here's the former, and a coil typically has somewhere between 100 and 400 turns. The wire is very, very fine, around about 10 microns, and the impedance means the AC resistance, is between 200 and 600 ohms. Now let's see what happens when we put them together, how the microphone is actually constructed. So I've just got to turn this page, it doesn't want to turn, here it is. Now, in a microphone, you've got the microphone capsule up at the top, a protective grill around the outside. This part, the handle where you hold it, is for the wires to go through, and there's a connector at the bottom. So this is what a microphone actually looks like. There it is. Now this is the microphone capsule. Here's the diaphragm, which is rigid, and on the edges it's flexible, so that means that this part can move up and down with the sound waves. You know that sound is a longitudinal wave. So when you get a high pressure part of the wave coming in, it pushes the diaphragm down. Low pressure pulls the diaphragm up. There's an air bleed hole. It's only small, but it just allows the air to move in and out. So that allows the diaphragm to move. Of course, the coil is attached to the diaphragm. So as the diaphragm moves up and down, the coil moves up and down in this radial magnetic field. And here's a photograph. It's not a very good one, I'm afraid, of what the diaphragm looks like when it's in the magnet. Okay, now let's have a look at the physics of it. This is the exciting bit. Now then, we've got north on the outside and we've got south in the middle. So as we said, it's a radial magnetic field. So on this side, the magnetic field points to the left. On this side, it points to the right. Now, if we look at the situation where the coil is moving down, so here's the magnetic field, here's the motion of the coil. If you apply Fleming's right-hand rule, you'll find that on this side the current is going into the page, and we show that with the tail end of an arrow. On this side, the magnetic field goes in the other direction, so with this moving down, we find that the current comes out of the paper, and we show that with the tip of an arrow. So in that situation, we can see we've got the north and the south pole of the magnet. Here's the coil. We'll see that the current flows anti-clockwise. And of course, when the coil is moving in the other direction, then the current flows in the other direction. So as the coil moves, we get this varying current induced in the coil. And the voltage is somewhere between 5 and 50 millivolts. So now you know how it works. You know about Fleming's right-hand rule. You know about a conductor moving in a magnetic field. Okay, let's just finish off by having a look at some typical data. So the frequency response of a typical microphone is between 80 to 15 kilohertz. 80 hertz, which is about low E on a guitar, and 15 kilohertz is getting up to the limit of human hearing. The output voltage, as we said, is between about 5 and 50 millivolts. And the impedance of the coil, impedance means the AC resistance, is between 200 and 600 ohms. And you can use Ohm's law, if you feel like, to work out the current. Ohm's law for AC isn't V equals IR, it's V equals IZ. Now, this is interesting. The polar response of a microphone is cardioid, and that means heart-shaped. Now, what we mean by that is that if we've got a microphone here, it's very good at picking up the sounds round about the front of it. It's okay at picking up sounds from the side, but it's very, very poor from picking up sounds that come into the back. And when we measure that and we plot it on this polar graph, we find 0 degrees. It's very good at picking up the sound. As we go round to the side, it becomes slightly less good, and then at the back it becomes quite poor. And if you think about it, that's really what you want in a microphone. You want it to be fairly unidirectional to pick up the sounds coming from the front. And this is a graph of the frequency response. At very low frequencies, it's not very good. You can see this line is pointing down. At very high frequencies, it drops off very, very quickly. But in the middle, which is where most of the music takes place, it's pretty good. For a double bass, producing sounds around this area, you'd use a different kind of microphone. But for anything from a guitar up to the very highest notes on a violin, you find that a moving coil dynamic mic is perfectly adequate. So there we go. I hope that that's been a useful use of 9 minutes of your time, because now you know how a dynamic microphone works. You know about the magnet, the coil, how it's put together, you know the physics of it, and you know some of the special language for talking about microphones. Thank you very much for listening. I hope it was a good 9.5 minutes of your time. Okay, Michael signing off now, wishing you all the best, and see you next time.